Okay, Assalamualaikum and good afternoon, everyone. So, again, today we'll continue with the talk supposedly on quantum field theory, but I will essentially, no, we're not going to field theory as yet, but we'll go into some what I call topic that was not really introduced in the undergraduate, which is second quantization. So, I'm not sure whether any of you have done second quantization at all. Anyone? Okay, never mind. So let me just share my slides. Where do you share this? Entire screen, I suppose. Okay, so let me go to the slides. Can you see the slides?
Yes.
Is it big enough? Because I'm not using Acrobat here because probably I want to.
Oh, annotate.
Yeah. Okay.
Okay.
As I said, we wanted to introduce something which is sometimes I do introduce, but sometimes it don't in my previous courses of advanced quantum mechanics. So I thought that one should just go into it, and then maybe after this talk, then we can go into quantum field theory proper. So let's go to the other slide. So essentially what we're going to do is to look at how you formulate many particle theory in quantum mechanics. Not necessarily relativistic in this particular case, but the intent was to go there, okay, to go to the relativistic cases and then have the proper mathematical tools. So so let me begin with this motivation first. Okay. So if we recall from our previous talk, we had the idea of relativistic quantum mechanics, sort of giving some extra solutions, which points to negative energies, and one could really interpret this as the negative energy C, for which one could interact with with particles from say with photons, for example, and then excite the states in the negative energy C, and then you find that this is equivalent to an opposite picture of an antiparticle, okay, going up. Uh, traversing in space and time, but in the opposite direction. Okay, so again, this is not quite. I mean, it seems artificial at this stage, but if you have done semiconductor physics before, then you probably have the same picture of the holes and electrons as the carriers of what do you call it? The charge transport. Okay, so let's just also try to justify this. How do you get the idea of many particle states in relativistic quantum mechanics. Essentially, one could sort of begin with the single particle Schrodinger equation and do perturbation theory. Okay, so you know perturbation theory involve. Can you see my cursor?
Yes.
Okay, great. So one could actually get this kind of terms, your perturbation theory. Okay, you'll find that uh, there's a denominator term which is depending on from the unperturbed energy to some perturbed energy. Me- okay. So and uh, the energy which is the perturbed energy, or well, essentially it's not the perturbed energy. I mean, is the energy of the other levels. Okay, there is no restriction. It's not really unconstrained. I should be careful in what I say. You have the other energy levels for which you can actually interact. So one of the things over here, one could consider this as large as possible. Okay, and then essentially you get intermediate states which involve other particles. For example, you can take the one electron system to begin with, and then you have n photons. Okay, so this, I think probably you have done perturbation theory, then you probably see that kind of things happening. But now, what's possible if the difference of energies, okay, is greater than the twice the rest mass energy of the electrons? Okay, one could now have intermediate states that include the electron positron pair. So you have enough energy to create this particle antiparticle pair. So in other words, once you include those possibility, then you have, okay, instead just one electron and then the photons, of course. You also have the virtual pairs of this electron and positron, the antiparticle and particle. Okay, so the higher the energy, then you can essentially have arbitrary number of photons and arbitrary number of electron positron pairs. So this is why we said in the previous lecture that we really need a many particle theory, and we need a different formalism to really describe the physics there. So okay. So let me just start off with the case of the classical case. How do you describe n particles in the what you call in the classical mechanics situation, for example? Well, we begin with the Lagrangian. One should actually start with the action, of course, but one can look at the Lagrangian to simplify things, and then essentially this can be given as the kinetic term minus some potential over here. And let me just denote, I think there's some missing subscripts here, but never mind. This is x dot nu here. Here, nu, basically I'm following the book by Planet. Okay, so I'm not changing the notation over here. So it's an unfortunate thing that he used nu because you can easily mistaken it to be the what you call the forward components. Okay, here it really means something else. Okay, so here it means the particle labels. So you have some of the individual kinetic energies, and then you have the potential energy that might depend on several different particles. So the many-body potential that is usually taken in most of the physics that we tend to analyze anyway would be just a single body potential, which one considers it as an external potential, or you can have a pairwise potential that involves two particles. Okay, involves the coordinates of two particles. Okay, rarely one goes beyond this. I think so far that I've seen, one goes to a three-body potential, and already you don't really have a nice intuition there, and probably my guess you lose some kind of locality in that sense. Okay, but that's for a different story. Okay, so yes.
If I may ask, the pairwise potentials is some sort like a coupling? Is it?
Well, you can think of the Coulomb
Yeah. So with
electron
directions.
repulsion potential. Okay, so in the normal case will be just the Coulombic repulsion between two electrons. Okay. So the external potential, one normally thinks is of the electron with the nucleon, for example. Okay. Is that all right? Okay, so the next, well, Lagrangian is not quite the language that we use in quantum theory. We go to the Hamiltonian formulation. So one writes down the Hamiltonian. Okay, so again here one uses the usual Legendre transform to get the Hamiltonian, and we'll be able to write this in terms of the momenta, the individual particle momenta, and then you have the the respective potentials that we introduced earlier. Okay, so that is the classical case. So now one sort of make it in terms of quantum state, quantum case. So one introduce operators, but really one has to understand what's going on. So it's, how should I say, one normally thinks the many body states or many body wave functions, they do not really correspond to the positions in space. Okay, they are really coming from a configuration space. Okay, which is a much more abstract notion. So that's why I consider this as sometimes can be misleading to some people. Okay, so what you have is that your x1 until xn, okay, usually we think this as the position of the individual particles, but now they actually label the quantum states. Okay, and of course there are conditions really. For example, in certain cases you would not want them to coincide, for example. So that's, so you can see how when you consider many particle system, there are there are things that you have to bear in mind. The assumption that you actually use in formulating this. And then what is this? Here I said take the position eigenbasis. Again, it's a sort of misleading idea. What you have is just the states of your configurations, okay, of the n particle system, okay, and the labels here might be corresponding to the spatial positions, of course, but then these are considered as degrees of freedom. So so one could think of if we have what you call three position coordinates to each particle, then your configuration space should be n cube. 3n cube, 3n, okay, 3n, and because these are considered independent, okay, then you have to multiply all the possibilities, okay. So that's, and that gives you the n cube thing. Is that right? Okay, probably it will be So you have 3n for each particle, three position particles um, for particle, and then you have n particles, and then you consider this as like labels, and then you consider like a Cartesian product, or in this case, it would be a tensor product. Okay, so you can see that the degrees of freedom is actually no becomes much larger than it's supposed to be, and
Prof,
yeah.
so when you write psi x1 comma until xn, so does it mean the usual tensor product structure like psi1 tensor with psi2, x1 tensor with x2, and etc., or this is something else?
Okay, there's a little bit of uh, uh, normally we think of being able to decompose your Hilbert space, and we try to decompose your Hilbert space into Hilbert spaces of the individual single particle wave functions. Of course, there will be then no. Sometimes you need constraints. You need to solve this. So yes, if you want to ignore all these technical complications. Does that answer your question?
Okay.
So that's why sometimes I think it's you give no physicists tend to think of it as just positions, but it's really more complicated than that. So now this state, which will later assume to be some kind of combination of single particle states. Okay, they have to obey. No, if you think of it as a basis, that means they have to obey completeness, okay, which I didn't write down, and then, if possible, you have to obey the autonomality condition. Okay, so in this particular case, because your x's are what you call continuous variable, then you have a direct delta function. Okay, products of that. Right. So, and if you want to express a general quantum state, so basically, you take the inner product of your eigenbasis with your general quantum state, and that now looks like what you call the many particle wave function. But again, no, the story is actually much more complicated. So, in many ways, there's a lot of modeling what you call aspects to this. So what you can actually assume. Okay, so we'll get to that a little bit later. Okay, so and then you can write down your Schrodinger equation. Okay, so you get your Hamiltonian from your classical case, and then just implement your position, so-called position representation of the momenta and so on. Okay, right. So one of the problems with the earlier formulation, the slide before, is that you're assuming you can actually trace out individual particles and you can actually follow them around, but not in the case of the particles that we often try to analyze, for example, the electrons. One can really distinguish the electrons uh, because they are considered identical particles. Okay, so there one should actually drop this aspect of distinguishability between particles. And how do you do that? We implement some permutation symmetry. Okay, so you have this quantum state over here. So you allow sort of permutation of these identical particles. Okay, and they are supposed to be obeying certain symmetry. Okay, which is the permutation symmetry essentially. Okay, the permutations, okay, if we repeat this permutation operator twice, the same permutation operator, okay, then you get the identity, okay, which is going to be important for us. So the permutation invariance, however, require you just need this kind of inner product to be. Suppose you have the permuted case, okay, two wave functions over here, two quantum states over here. The permuted case should be just equal to the unpermuted case. Okay, so over there, essentially, that tells us, okay, the only way that you can have this is to have a phase vector in front, connecting the permitted case with the original unpermitted case. And because of this square of this permutation operator is actually the identity, then one forces this phase vector to be just simply plus or minus 1. And that's why basically your wave functions for the normal particles are just either totally symmetric or totally antisymmetric. Okay. So this will connect with the idea of spins later on, but we are not. There is a spin statistic theorem saying that, okay, the antisymmetric case belongs to fermions, the symmetric case would belong to the bosons, but that would actually require quite, the proof of that is actually quite difficult, okay, done by a mathematical physicist. So, but let's just move on so that get somewhere. So, so how do you build, say, a fully symmetric wave function, for example, totally symmetric, sorry, is to think of, okay, first you probably want to simplify this wave function into some kind of product of a single particle wave functions. Okay, then this single particle wave functions, so you can start to to do the permutation symmetry. Okay, so in this way, again, this is actually a simplification. So one could think of a possibility of failure in these particular answers. Okay. Anyway, okay. So to get the permutation symmetry right, for the case of the bosons, for example, which requires a totally symmetric wave function, then you do a symmetrizer, you which involve the permutation operator, the previously the Tij, but now Tij now goes with all the pairs that's possible. Okay, and then implement this symmetrizer operator onto your single, the product of single particle wave functions. Okay, so then essentially you get your wave function for your particles. Okay, I think this is quite simple. I think I've actually done this in the second course of quantum mechanics. So similarly, for the case out of fermions, you require a totally antisymmetric wave function. And in this particular case, you use an antisymmetrizer. The difference between the symmetrizer and antisymmetrizer is this factor epsilon p, which can be a plus or minus 1, depending whether the permutation is actually an odd permutation or even permutation. And again, now, given that you have this antisymmetrizer, and then you antisymmetrize totally on this product of the single particle wave functions. And that the resultant of this can be actually written as a determinant, as you have probably seen in the second course of quantum mechanics. Now, why do we want to do this? Essentially, is that first, of course, you have the permutation symmetry that must be obeyed by the particles themselves, but you also make simplification of the dimensionality of the Hilbert space. Okay, so that is another thing. You probably can see this from the point of view of, let's say, spin states. You have two spin states, then if you take the tensor product two spin states, then basically the dimensionality is actually 4, but you can break it down into the antisymmetric part, which is dimension 1, and then the symmetric part, dimension 3. Okay, so you reduce the dimensionality of the Hilbert space. Now, it's one of the problems with the previous formulation is that you need to symmetrize and anti-symmetrize with respect to the so-called position variables, whereas that is not the natural way to describe the quantum states. Okay, because position is less natural. Okay, I can't really find the words for it. A better way is to look at the number of particles. Okay, so this is where you need a different kind of formulation of the quantum mechanics, and you probably have seen one formulation that involves the creation and annihilation operators. Okay, so here we assume that we can use this. Okay, so what's going to happen here is that, okay, you have the creation and annihilation operators obeying this. I'm trying to use this. Just bought a new tablet. Let's see if I can write on this. Where is it? Okay. I'm still trying to learn with the tablet here. So you learn about annihilation and creation operators when you use harmony oscillator. Sorry for the small handwriting. I'm trying to get used to this tablet. So, but here you don't really need this. All you need is essentially, in the case, even in the case of a harmony oscillator, the basis of this algebra, I think I better not use it. The basis of this algebra is essentially is the Heisenberg-Weyl algebra. Okay, so you can combine your operators using the usual definition of creation and annihilation operator. Okay, and it doesn't need that potential. If you know what I mean, the potential harmony oscillator does not need to be there. You can still recreate this algebra, and basically it comes from the Heisenberg-Weyl algebra. So one can actually do this now, but now with the interpretation is not increasing the levels of energy or anything like that, but now you have the natural interpretation being the counting the numbers of particles. Okay, the only thing that one needs to do here is now to append to this algebra some kind of labels that actually tells you where the particle is. Okay, so you need the modification that we want to do is that these operators, okay, will be labeled by their spatial dependence. Okay, so now what is the resultant algebra that you're supposed to have is the following. Okay, you get the same thing for the trivial commutation over here, but for the non-trivial one over here will now be replaced by well, in this case will be a direct delta function. Okay, depending whether it's your x coincides with x dash. Okay, so if it's not, then it will be 0. So meaning for x and x dash being different, okay, the commutator of a and a dagger will be just 0. The case
Doctor,
yeah.
Doctor, can you remind me what the direct delta functions with the superscript 3 because of what?
Okay. The best, because we are thinking. Remember that this axis. Oh, sorry, I'm not used to this. Where is this my pen over here? Okay. Your delta 3 here is the simplest case would be if you just use your Cartesian coordinates, your delta 3 will be just your products of your delta x minus x dash, delta y minus
and then z. Oh, okay.
But you have to be careful because one can use different coordinate system. The definition will be altered slightly.
So over here, if your delta 3, your x is equals to x dash, then it gives you 1.
No, it is your direct delta function. Okay, we would like to make it 1, but unfortunately
But
not.
then?
Okay.
Okay.
The way it's been done, it has to be defined under an integral. So,
okay.
for example, the total number operator, okay, which now will have the combination of your creation operator with your annihilation operator at the same point.
Okay.
So if you do this, then really there is a delta function in this particular expression. So you need to integrate it.
Oh, together with the delta function.
Okay, so in that way, then you'll be able to remove the direct delta function, and then essentially it simply counts the number where the particles are. Okay.
Oh, okay.
It's integrated over all space.
Do you have an example for that one?
Oh,
never mind. Let's run. Thank you.
This is more conceptual. Okay, so but really you can think of suppose you have say sorry, my cat is making noises. Can you hear that?
Yes.
Okay.
I can hear.
Uh,
And then so let's say we have 2 particles or
okay, let's say 2 particles in the volume. So that means the position of one particle will be at some point. So it will have a direct delta function there, and then the other particle will have another direct delta function there. Okay, but now you are going to integrate over all possible x. I hope that makes sense. Anyway, okay. I think we want to gloss over the technical problems. Okay. Essentially, we want to just introduce the concepts.
Okay.
Is that okay? So that's why you have that integral over here. So basically, it counts the number of particles in that space, and for our purpose at the moment, your number of particles actually is fixed. That's the reason why we want to move away from quantum mechanics, the non-relativistic version one, okay, to the case where your number of particles is not fixed, like the one we mentioned the first slide. Okay, so that will need some kind of field theory. Okay, so now one defines the states for the n particle Hilbert space. Okay, basically you build this using your so-called vacuum state. Okay, the vacuum state is written as 0 here. Okay, and the definition is essentially that there is no particle in that state. Okay, so if we put n0, okay, the number what you call the number operator there, then basically it counts to give you 0. But another way of thinking about this is to define it just in the same way we do for the harmony oscillator, is that the annihilation operator acting on the 0 state will give you 0. And then you have the Hermitian conjugate of that equation. Okay? But that state will be normalized. Okay. So over here, one can now start from that particular state and generate other states, okay, to give you the sort of localized state of n particles. So this is different from the way we think of the harmony oscillator. Okay, so now we are actually generating particles, okay, rather than moving from one energy level to another. Okay, and this so-called Hilbert space of localized states, if you like, okay, is sometimes called the second quantized Hilbert space. Okay, and in this case, it's for the bosons. How do you get that fully symmetric version of that state? Is because that your creation operators obey the previous algebra. Okay, so that guarantees your the necessary permutation symmetry of your n particle state. Okay, I think I'm getting to the end of it. So today we finish earlier. Okay. So the next case will be the case of the fermions. I don't have a nice way to introduce it, but no, you need to modify the algebra a little bit. Okay, by using what we call anti-commutators. Okay, so the operators, the creation operators and the annihilation operators are now what we call fermionic operators. So instead of having the algebra defined by commutators, they are now defined by an anti-commutator. An anti-commutator is given by, say, between A and B is given by just your symmetrized version of the operators. Okay, and one should also need to be able to define. Remember, the operators are supposed. When you do all this, you have products of operators. One should be able to find a modification to the Leibniz rule. Okay, remember the Leibniz rule is like the derivation property. Okay, so here what happens is that there is a mixture between commutators and anti-commutators. Again, I don't have a very nice way to actually introduce this. Okay. So, and one of the exercises, usually this is given in the second course of quantum mechanics, you can actually show that the fermionic operator has only, fermionic number operator has only eigenvalues 0 or 1. And that is essentially reflective of your Pauli exclusion principle. And I'm supposed to have another slide. You can actually show that what you get is a fully anti-symmetrized what you call wave function from this kind of annihilation and creation operators. I think this is my last slide. Sorry, I didn't get to prepare much. So I think I welcome questions. All of these are actually taken off from the book by Kleiner. Okay. Kleiner does a lot more things inside there, so I'm not skipping some of the stuff which I think is not quite necessary. Okay, I think that's somebody. Sorry, is there a question here?
Yes, one. Does second quantization sama macam the quantization or is there the name of concept?
Is okay. You don't actually see it here. What happens? There are various ways of introducing second quantization. One of the other way to think about it is that previously your wave functions, okay, wave functions are not observables. Now they can become operators. So that is where the second quantization comes in. So previously you think of the wave function as simply the states, just functions. Okay, now they themselves become operators. So that's why it's called a second quantization in that context. Okay, over here I've not gone to that part. There is one section of Kleiner's book that actually talks about, okay, the operators themselves will get another operator version using the creation and annihilation operators.
So there is a super operator.
No. It's not super operators. Basically, because here it's just like the same type of operators, but now they act on infinite dimensional space. Okay, so that's essentially. You have to remember. Okay, there is no client treat this quite in detail. Remember the localized labels. Okay, so there are infinite number of them. You know? So in other words, you are actually changing the Hilbert space to a different space. Then okay, the next step would be is rather than talking about those labels, we talk about the occupation numbers. Okay, and I think I believe I've introduced this once. So you talk about okay, for this particular energy state, how many how many particles actually occupy that energy state. But now, no, you have to. We are now sort of making the transition going from states in the ordinary context to states that depend on the coordinates. Is that clear, or am I getting confused? Meaning there's a continuous variable that's sort of running through the Hilbert space. Okay.
This might sound stupid, but isn't the original Schrodinger equation already has like the position and moment, the position and the time?
Yeah, but okay. How should I say this? Okay, even in quantum mechanics, basically there is already infinite dimensional Hilbert space. Okay, because you have your position variables already there, but now this thing gets more complicated with the case of the configuration space. Okay, in the quantum mechanics case, normally you think of the Hilbert space there is basically from one particle state. Okay, now instead of one particle state, you have to consider the n particle states. Don't know. I'm not very. My eyes are getting a bit. Uh, does that answers your question, or there's
Yes, I think
there's
so.
really little difference at this stage? Okay, really little difference between the wave functions that you see in the one particle state with the n particle state, because now you should be considering your n particles are not, sorry, your n positions of the n particles are not just coming from the same, what's the best, the configuration space of n particles is not the same as the spatial position of a single particle. You get what I mean? It's like
I
like
can roughly
you're
understand.
multiplying the possibilities with n times, depending on the number of particles, because you have your degrees of freedom is now amplified with respect to the number of particles. So the other things, I have something in my eye, sorry. That's why when we talk about what you call n particle wave functions, one has to be really careful about identifying those labels with the space themselves. Okay, it is related to the space themselves, but one should be really thinking of those variables as something separate. Okay? It's just like you take the Cartesian product of three positions. You know what I mean? Okay, so you have x1, y1, z1, x2, y2, z2, x3, y3, z3, and then you have the Cartesian product of those. So the space of that is now the configuration space. So the variables themselves are not really referring to the I mean, they refer to the original space, but the number of degrees of freedom is there is unlike the ones that we think of, say, for a single particle. Okay, I'm not explaining this very clearly. Okay, the other thing that probably one needs to be careful about is the case of the indistinguishability. Okay. Now, imagine trying to quantize this thing, for example. Okay, then if one were using the ordinary quantization, then you probably need to be careful when precisely you want to put the permutation symmetry in, before quantization or after quantization. Okay, so there are those kind of problems coming in. Sorry, my eyes getting a bit dry, I suppose. John, I'm not explaining this very well, but I hope you have some idea. Do you understand the difference between the configuration space and the real space?
Okay, so then this I'm not so sure whether this is the right question or not, but in the case of quantum computing, so why don't we usually consider the idea of position in this case?
Because we don't need to, because we are only concerned with the spin quantum numbers.
So meaning in the case of quantum computing, we don't really have like the distinguishability problem.
Indistinguishability problem is we have that actually. That's why people are now talking about looking at the fermionic cases, right? But normally when one thinks about the spin, okay, one of the things over here, there's another complication that comes in. The Hilbert space can decompose. Okay, you can decompose into the spin degrees of freedom, and then you have the spatial degrees of freedom. Okay. So for the spin degrees of freedom, you still can have, even for fermions, you still can have symmetric case for your spin, provided the spatial degrees of what you call spatial degrees of freedom will be antisymmetric for them. Then you have the total wave function to be antisymmetric. So in a way, there you can get away without considering all this complication. But I hope you understand. I'm not sure how to explain any further.
I think I more or less get it.
Perhaps what I'm trying to point out is that there are problems when you do this transition to field theory, because later on you probably even forget about states. We'll just talk about the field variables, the fields themselves, which are now operators. Okay? That's the transition that we're going to make. If I use a different way of describing second quantization, now you are concerned with those wave functions that has now become operators. Which is not very clear from the way we introduce here, because I'm following Klein. Okay, maybe if
Could you show the name of the book again?
the name of the book, maybe I stop sharing. Is that okay?
Okay. Or you stop.
On the slide, I mean, sorry. Okay, maybe I show you on the slide. Where is it? It's a huge book. I've not really read it. I was trying to go page by page. It's just bogs me down. So I had to sort of quickly read for today's lecture. Where is it? One before or after? Before. Yeah. Can you see that? At the bottom. I can show you the book if you want. It's my. Can you still see my camera? It's this book.
Currently, I'm looking at the slide.
Okay. My
Yes.
my cam is still visible.
Yes.
So it's this book.
Purple, right?
Yeah.
This is the book that you cannot lay down.
You can die
You can.
from reading this book. It's just if you go to sleep and then the book just bang your head.
Unless you have to.
Another book of that nature is Gravitation, Mr. Ton and Will.
Oh, that one.
You can't read
Heretic.
lying down.
Oh, doctor, so it's like for many body particle, it's like when you're doing DFT, your states become operator, is it? It's, I think the concept is similar, or?
In a way. Okay, I mean, how should I say? Okay, maybe I just point out to which section we can get this book. Later on, there's a section of this book. Where is it? Section 2.5 of Planet's book talks about second quantization. Okay, where you take any particular operators, okay, and then you sort of rewrite it in terms of the creation and annihilation operators. In other places, no, the way I've learned it in with Professor Hurst last time, which also I do not quite understand at that point in time, is that the wave function, the states becomes, okay, the wave function becomes operators, just because of that possibility of putting all the creation and annihilation operators.
Okay, so if I get it correctly, if the wave functions treating like an operator, so there is a commutations and anti-commutations for the wave functions.
Yep.
And then the operators, so the observables will be like what? Which will represent the observables?
Okay, maybe one possible thought is to think of Kleiner also did is, okay, remember the localized algebra?
Uh-huh.
Okay, instead of the local variables of position, for example, now you define this on the lattice. Okay, so this is just like people doing solid state physics, and then your labels become dependent on the lattice sites. So now I can talk about, say, some Hamiltonian. In the case of kinetic energy, sort of destroying one particle on one side and then create a particle on another side, as an example. Okay, so there you can actually start to do. I'm not quite sure. Let's see if I have anything on my laptop.
Doctor, you want to start recording or?
Yeah, I think I better stop because I do not want to write this too much. So let me stop it first.
Oh, Chong only have 1 hour. Is it?
No, sorry. See, I can't remember now. It's been a long time since I used it. So where is my thing? So I stop recording. Stop. Where stop? Stop presenting. Stop. Can't find the stop recording. Sorry. I'm not used to this. Manage recording. Okay. So now stop recording. Okay. So that's it. I hope I'm not explaining this well because I didn't quite prepare, because I didn't go into details. I'm still in chapter 1 when reading this book. So the second quantization is in chapter 2.